Welcome. This is a lecture about congruences. I'm going to start by illustrating the basic idea with an example. Let's consider days of the week. So suppose, for the sake of discussion, January 1st occurs on a Sunday. Then a natural question is, what day of the week is, for example, January 8th? Or any day of the year. Let's just number the days 1 through 365. I don't care about the months. So what day of the week is the 100th day of the year, for example? Or finally, how about January 1st next year? What day of the week will that be on? That's not hard to do, and I'm doing it here as an illustration of the idea of congruences. So you start with the first day and you number the first 7 days. That's the first week, 1 through 7. And you label them Monday through Saturday. And then, okay, the first question was the 8th. Well, you have to add one more day, and that starts over at Sunday. And so that says that the day of the week, January 8th, occurs on a Sunday, just like January 1st. So what about the 100th day of the year? Well, we know what the Sundays are. The 1st and the 8th are Sundays, and so is the 15th. And you just keep adding 7, and all of those days are Sundays, the 36th and so on. You keep going, 64th, 78th, 85th, 92. And then finally you get the day number 99. These are all Sundays. So since 99 occurs on a Sunday, that means that day 100 must occur on a Monday. All right, I think you all know how to do that. Now, mathematically, what have we done there? Well, the idea is we did the division algorithm. We divided 7 into 100 and wrote it as 7 times 14, which is 98, plus a remainder of 2. And the remainder is what matters. So we look at this remainder 2, and we see that that's matches up here with Monday. And that's the way the calculation works. It's a simple application of the division algorithm. Okay, well, let's do the last one. What about January 1st next year? Well, counting the days, the last year of the year is day number 365. And the first day next year, you add 1 to that, so you get 366. And let's see, if you do the division algorithm, 366 is 7 times 52 plus 2. Easy to check, 52 weeks in the year, but there's these extra 2 days. And so that says that January 1st next year will be on a Monday. And again, what matters is the remainder when you divide by 7. And what this says is that the calendar regresses 1 day every year. The January 1st goes from Monday to Tuesday to Wednesday, except, of course, in leap years, and never mind leap centuries and so on. So as I said, what matters if you want to know the day of the week of day n is you do the division algorithm. You write n is 7q plus r, and r is what matters. The day is given by, the day n is the same as day r, because they differ by a multiple of 7. And in the division algorithm, you can arrange that r is between 0 and 6. And 0 through 6, that's 7 numbers. Those are the 7 days of the week. All right, so here's a definition which captures the essential idea there. Let's start with an integer m. And it's an integer, and we assume that it's greater than 0. And here, this is the definition. We say that A is equivalent to B mod M. A and B are integers, and we say that they're equivalent to each other mod M if the following condition holds: if M divides A minus B. All right, easy enough. So in the case of weeks, M was equal to 7, and we're looking at when integers, their difference is divisible by 7. Another way to say the same thing, to say that M divides A minus B, is simply to say that A minus B is a multiple of M for some integer k, and just by bringing the B to the other side, another way to think of it is to say that the integer A and the integer B, they're related to each other by adding a multiple of M. And a little bit of notation for this is we write A triple line B parentheses mod M, and you read that A is equivalent to B, and then in parentheses the mod M is indicating that it's with respect to this number M, which is called the modulus. So let's do a simple example. Take M is equal to 2. What does it mean to say that A is equivalent to B mod 2? Well, as I said, that means that 2 divides A minus B, and if A and B are the same parity, then their difference is divisible by 2. So this holds if and only if they're the same parity, either both even or both odd. So equivalence mod 2 captures the notion of parity. So, for example, if A is even, then you write it as 2k plus 0, and that's the same thing as saying that A is equivalent to 0 mod 2. Whereas if A is odd, you write it as 2k plus 1, and you see that in this case A is equivalent to 1 mod 2. So that's the R. When you do the division algorithm, you get either 0 or 1, and you see that every integer is equivalent mod 2 to either 0 or 1. If it's even, it's equivalent to 0, and if it's odd, it's equivalent to 1. Okay, here are some basic properties of the notion of modulus. So we fix a modulus M, and suppose we have an integer A. Then one thing is that A is equivalent to R mod M for some number R between 0 and less than or equal to M minus 1. We've seen that already. You do the division algorithm and you take the remainder. And this R that you get is unique. That's the division algorithm. There's a misprint here. I called it the Euclidean algorithm. It's just the division algorithm. You write A is equal to QM plus R, and R is between 0 and M minus 1. And that says that QM is equal to A minus R, which says that M divides A minus R. And that's exactly what it means for A to be equivalent to R mod M. All right, so that's a elementary property. Now, there's a little bit of a subtle notion here. That's the notion of congruence class. And let me illustrate this with an example. Take the case when M is equal to 2, well, so we saw that all of the even numbers are equivalent to each other. Every one of these numbers is equivalent to 0 mod 2. And then, on the other hand, you have all of the odd numbers, and those are all equivalent to each other, and they're all equivalent to 1 mod 2. And you're all familiar with the fact that the set of even numbers can be written as the union of the even numbers and the odd numbers. Now, if you do the same thing, for example, with m is equal to 7, well, you get the following numbers are all equivalent to 0. These are all of the numbers, all of the multiples of 7. And that's what we call a single congruence class, all of the numbers which are equivalent to each other. And then if you take 1 and add multiples of 7 to it, you get a whole bunch of numbers. All of these are equivalent to each other, and they're all equivalent to 1 mod 7, and so on. And you can keep going all the way up to 6. You can take the number 6 and add multiples of it, and so on. And these lists of numbers that I have now in braces from 0, 1, 2, 3, 4, 5, 6, these are all sets, and they're all disjoint, and their union is all of the integers. That is to say, the integers, there are 7 of these classes, and these correspond to the days of the week. And the congruence class is this infinite set, all of the numbers which are equivalent to each other. Now, we're not going to talk too much about congruence classes. We usually just sort of think of them in terms of their smallest representative, this number 0 through 6. But sometimes it's important to think about the entire conjugacy class. Okay, here are some properties of modular arithmetic, as it's called. So you always work, well, almost always work with a fixed modulus. So let's fix our modulus, m, and let's take some integers a, b, and c. Now, one thing that's obvious is that a is equivalent to a mod m. And another thing that's almost equally obvious is that if a is equivalent to b mod m, then b is equivalent to a mod m. These are familiar properties of numbers. They hold for this notion of equivalence. And if a is equivalent to b mod m, and b is equivalent to c mod m, then a is equivalent to c mod m. So these properties are sort of like saying that equivalent is like equals. The properties of equals that you're familiar with apply here. And let's prove these. The first one, m obviously divides a minus a, which is 0, so that says that a is equivalent to a. And clearly m divides a minus b if and only if m divides b minus a, because b minus a is just minus a minus b, and so you just switch m to minus m. And the last one just requires a few more characters. If a is equivalent to b, then that says that you can write a minus b as some constant k1 times m. And if b is equivalent to c, that means that you can write b minus c as some other constant times m. And then if you just add these two, a minus c is equal to a minus b plus b minus c. And that's equal to, let's see, this first one is k1m, and the second one is k2m. And so you get a minus c is k1 times m plus k2 times m is k1 plus k2 times m, and therefore m divides a minus c. Okay. All right, I want to look at a couple of more properties. And basically what these properties are saying, just sort of loosely speaking, is that you can do arithmetic mod m, and it's very much like just doing ordinary arithmetic with integers. Various laws like the associative law and the distributive law and the 0 and the 1 and so on, the properties that you have in ordinary arithmetic apply to arithmetic mod m. So for example, what's certainly true is that a plus b mod m is equal to b plus a mod m. If m divides a minus b, then if m divides a plus b, it divides b plus a. Similarly, m divides a times b if and only if m divides b times a. So addition and multiplication are commutative, mod m. The most important point here is one that I've kind of glossed over, and it's the following. Suppose a is equivalent to b mod m, and c is equivalent to d mod m. Then what I'm saying is you can sort of think of a and b as being equal mod m, and or maybe a better word to use is the same. To say that a is equivalent to b mod m, and similarly c is equivalent to d mod m, means for all intents and purposes, if you're doing things mod m, it doesn't matter which one you use. So in particular, if you wanted to add a plus c, that would be exactly the same thing as adding b plus d mod m. So on the left-hand side, I have a. I could have switched it with b, because they're equivalent, and c, similarly, I can switch it with d, and it doesn't matter. I get the same answer. And similarly with a product. If you a times c, you can replace the a with b and or the c with d, and you still get the same answer. Okay, let's do a simple example of this just to illustrate that I'm not talking nonsense, but I'm also not talking triviality. There's a little bit going on here that might not be obvious. Let's take m is equal to 5 and look at 3 plus 7 mod 5. Well, that's 10 mod 5, and if you divide 10 by 5, you get 0, so that's 0 mod 5. Now, 10, of course, is not literally equal to 0, but it is equivalent to 0 mod 5. Now, instead of 3, what if I'd used 8, and instead of 7, I'd used 17? Well, 8 and 3 are equivalent mod 5, and 17 and 7 are equivalent mod 5. So what I'm saying is it shouldn't matter. I can replace 3 with 8 and 7 with 17, and I should get the same answer. Well, when I add them, I get 25 mod 5, and that is indeed 0 mod 5. Of course, 25 is not literally equal to 10, but that doesn't matter. 25 is equal to 10 mod 5, and because they're both 0 mod 5. And similarly, 3 times 7 is 21. Well, what about 8 times 17? That's 136. Well, 136 is 135 plus 1, and 135 is 5 times something. And so we get the same answer. 3 times 7 mod 5 is exactly the same thing as 8 times 17 mod 5. Here's another example which illustrates this, and this example is a little bit less, shows you the power of this a little more. What if I asked you to compute 2 to the 10 mod 3? Well, you write down 2, 4, 8, 16, 30. You keep squaring, take all the powers of 2 until you get up to 1024. That's 2 to the 10th. And you then compute 2 to the 1024 mod 3, and it turns out that this is 1024 is 3 times 341 plus 1, and so therefore that's equivalent to 1 mod 3. So the answer is 1. But here's a better way to do it. When you square 2, you get 4. And rather than going on, you can reduce 4 mod 3. 4 is equivalent to 1 mod 3. So you might as well replace it, since you're at the end you're going to do that anyway. And then you double it, and again you get 2, and then 4 again, and then you replace the 4 with 1. In other words, when you keep doubling 2, you get this sequence of numbers: 2, 1, 2, 1, 2, 1, 2, 1, 2, 1. And last time you get 1, and that says that 2 to the 10th is equal to 1 mod 3. All right, the point is that when you're doing a big calculation, each step of the way you can reduce the numbers mod 2. And so these big numbers that might look like they're coming into the calculation, mod 3, or whatever mod you're doing, they don't really matter. Okay, so suppose A is equivalent to B mod M, and C is equivalent to D mod M. This is what I was just talking about, but I want to state it formally as a theorem. Then we conclude that A plus or minus B and C plus or minus A plus or minus C and B plus or minus D are equivalent, and A times C is equivalent to B times D mod M. I'm just summarizing what I talked about in the previous couple of slides. Now, what about division? Suppose A times C is equal to, or is equivalent to, B times C modulo M. Can you do cancellation? Can you divide those C's and conclude that A must equal B mod M? So, let's do an example. Suppose M was equal to 9, and I looked at 3 times 3. 3 times 3 is equal to 9, and that's 0 mod M. Notice 3 times 6 is 18, and that's also 0 mod 9. And that is to say that 3 times 3 is equivalent to 3 times 6 mod 9. Both of these things are equivalent to 0. Now, I want to know whether I can cancel the 3's from both sides of this expression and conclude that 3 is equal to 6 mod 9. That's the question. And the answer is no. So something went wrong here. Just you can't cancel in the way you might have thought you could. And this is an important point. Now, the problem with this example is that we're working modulo 9, and 3 divides 9. And you can't divide by 3 modulo 9. And, well, that's what I just illustrated here. And the issue is, the problem is that 3 divides 9. So here's the theorem. Suppose I know that AC is equal to BC modulo M, some fixed M. I'd like to know if I can cancel the C's. Well, I just saw in the previous slide that you can't necessarily, but if you assume that C and M are relatively prime, then if you have this extra assumption, then you can cancel the C's and conclude that A has to be equivalent to B mod M. All right. So in the previous example, this failed because the GCD of C and M was not 1. And the fact that this is true is really elementary. If AC is equivalent to BC mod M, that says that M divides AC minus BC. And that says that M divides A minus B times C. And now the crucial point is that if M and C are relatively prime, since the GCD of M and C is 1, that means that this M has to divide A minus B. And that is to say, that implies that A is equivalent to B mod M. And what we found is that you can cancel provided C and M are relatively prime.